acting on the object, okay? So, and then they are vectors. So make sure you have appropriate scales for the length of each forces and then their correct directions, okay? All right, but do not include the net force, okay? Now, the third step here is to resolve all the forces into X and Y components, okay? So because you have X and Y coordinate system, then you'll be resolving them into X or Y components, okay? And then the fourth step is draw a separate free body diagram for each object. If you have several objects in the problem, okay, and then you are interested on those different objects, then you'll need each object will have a free body diagram. Now the exception is if you treat the object as one system. If in that scenario, okay, then you just need one free body diagram for the whole system, okay? So we will talk about it later. Probably later in the chapter, maybe in another class, not today's class, okay? All right, so let's take a look on a couple examples here that how you want to draw the free body diagram on those two scenarios. So if you have a box resting on a horizontal surface, okay? So in that case, you can think about how many forces will be acting on the body, right? So there will be the weight of itself because it's near the surface of the earth, okay? So one thing to keep in mind, everything near the surface of earth will have a weight, a force on it, the gravitational force by the earth, okay, on it, okay? So the weight will be always there on any object near the surface of the earth. And then because this guy is resting here on the surface, so the surface is supporting it, okay? So then that's that force, we call it, use the symbol M, because usually we call that normal force, okay? So we'll talk about that later as well. But for right now, just know that it's a force, okay, M. All right, so then in this scenario, you have two forces on this object, right? This is your free body diagram for the object. So the dots represent the box, the weight goes down, and then the supporting force goes upward, okay? So because the box is resting over there, so these two should have about the same, or should be equal, should have the same magnitude, okay? So when you draw it, make sure you have about the same length for the two vectors, okay? A second example here in this figure is a box is resting now on an inclined surface over here, right? So then in this scenario, you can think about there will be a normal force, okay? So this is your object over there. There's a normal force, okay? And then there's a weight pulling it downward, okay? So for weight of the object, it's always going to be downward because it's in the same direction as the gravitational force. It's the gravitational force on the object, okay? So it's always going vertically downward, all right? Now, because it's sitting on the surface over there, then there will be a contact force between the surface and the box, okay? Pointing in that direction, okay? So again, that's a normal force, so we use the letter M for that. And then because it's resting over there, so then there should be a friction force, okay, to prevent the box from moving, sliding downward, okay? So there's a friction force there as well, okay? So if you consider all the scenarios, so then those are the three forces acting on this object, okay? So 1, 2, 3, okay? All right. And then we will be probably showing you some more examples on how to draw free body diagram when we are doing actual problem solving, okay? All right, so the next one here talks about development of the force concept, okay? So if you are pulling an object or pushing an object, then you are giving the force, okay? A lot of times you can use a scale or a spring, okay, to do that. So if you have a scale, it's pretty much, it could be made of the spring over here. So when you pull, spring will be stretched or compressed, okay? So in that scenario, then there will be force exerted by the spring, okay? And if you pull it, all right, and then if you let it go, then spring will go backward. It has a tendency of going back, okay? So or returning to its initial position. So that force is called a restoring force. Okay, that's will be proportional to how much the spring is being compressed or stretched. Okay, but we'll probably talk about spring force later on. Okay, so for right now, just you just need to know like if it's being stretched or compressed by a certain amount, then the force as a result should be proportional to the amount of x. Okay. There are other types of forces, like one will be the weight, okay, and then one will be the contact force if there's contact between objects. So if you are sitting on your chair right now, there should be a contact force between you and the chair, okay. So this will be supporting you upward, okay. So you can call it like T. And then on this guy over here, on the floor here, there should be supporting force onto your feet as well, and then on your arm over there as well. Okay, so there are different forces. If you are looking at the all the forces on your body, then you think about those different forces. Okay. um, so among those different forces, they are actually divided into two categories. Okay. So one is called the contact force. So for example, for this C, T, and F, this C, T, and F, they are based on you have a contact between two objects. Okay. Now for the weight, the gravitational force on you, you might be um, you might not necessarily have to have contact with the earth. Okay, so for example, if you are traveling on an airplane, okay, so then your body is not in contact with the earth, right, because you are flying. So then but you still have gravitational force on you, so you still have weight. Okay, you still experience the gravitational force. So for those type of force, they are called field force. Okay, or um, later next semester when you guys talk about electromagnetic wave, if you have two charges, they will have interaction between each other, but they don't necessarily have to be in contact to have that force. Okay, so those forces are called field force. Okay. All right, and then more broadly, in science, there are four different forces, okay, or four different fundamental force fields, okay. So one is gravitational force, okay, and then electromagnetic force, and then strong nuclear and wake field forces, okay. So those the later two, they are related to nuclear physics, okay. All right, so those are different forces you might encounter. So as force is a vector, so then you'll express force in vector form. Okay, you'll have an x component, y component if this is two-dimensional force. If it's a three-dimensional force, then you have x component, y component, and z component. Okay, and when you are looking for all the forces on the object, okay, so then the collective effect will be you will have a net force on the object. Okay, so then simply you will sum up all of the forces acting on the object. If there are two forces, you add two up. If there are more, then you add all the forces up. Okay, but keep in mind you should be doing this in vector form. Okay. All right. So we'll take a look on this example here. So I think we have talked enough about like vector addition and stuff. So I'm going to just show you guys quickly of the solutions on this one, okay? So because we have someone that is online today, I'm going to be using this here. Okay, let's take a look on the problem here. So the problem says you have two ropes are attached to a tree, forces of F1, 2.0 I plus 4.0 J, and then F2 equal to 3.0 plus 6.0 J, okay? These two forces are on the same plane of X and Y plane here, okay? What's the resultant force of the two, okay? So you're basically going to be doing, let me see. So the resultant force would be equal to F1 plus F2. All right, and then you'll be doing the components up, adding up their components. So for the X component will be F1 X plus F2 X. For the Y component, our resultant will be F1 Y plus F2 Y. Okay, so let me see. So F1 is 2 and 4, and then 3 and 6 for F2. So when you do X plus X, there will be 5. Okay, so 2 plus 3, that is 5. And then 4 plus 6, that's 10. Okay, so for the two components. So your resultant force is equal to 5.I plus 10.10J. Okay, so this is your resultant. All right. And then for the magnitude, you'll be doing square root of 5.0 square plus 10 square, right? So they give you 11.2 newtons roughly. Okay, or 11 newtons. Okay, so just keep in mind in part A, because it's asking you what's the resultant force of the two. So that's asking you the vector, right? Because force is a vector. Okay, so you can either express in the X and Y component like we did, the 5.0 I plus 10J, or you have to find the magnitude and directional angle first. Okay, and then the directional angle, yeah, directional angle, I guess I forgot about that, but it's tangent inverse of 10 over 5. Okay, so that's tangent inverse of 2. I guess I forgot to do that. Let me see. Have a double quick check on that one. So A tangent of 2 in degrees. Okay, 63. So directional angle will be roughly 63 degrees. Okay, on that one. Or here. Yeah, but you guys can write this down, right? All right. So we tangent inverse of 10 over 5. Okay. All right. So that's a quick example on the force concept there. The next section here talks about Newton's first law of motion. Okay, so the first law of motion says that an object will continue in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by a net force. Okay, so it's a long sentence, but in short, you can put it in another word. It says unless there's a net force on the object, the velocity will not be changing. Okay, so if it's in a state of rest, that just means the velocity is equal to 0. Okay, so then it will remain as 0. Or if it has a motion at constant speed along a line, so that means the speed is constant or the velocity is constant, okay, in a straight line. So either way, okay, it remains its original velocity. Okay, so if there's a net force, then the velocity will change. Okay, unless there's the net force, the velocity will not change. Okay, so Newton's first law is also often referred to law of inertia. So basically says the object is very lazy. Okay, if it's not being pushed by a force, then it will not change its status. Okay, sometimes like us, right? If we are not forced to do something, we will not do it. Okay. All right. And then so the object is lazy because it has mass, right? Because mass is the measurement of how hard it is to changing an object's velocity. Okay, you can imagine if the object has larger mass, then it's not easy to, or it's not as easy to change its velocity, right? If you push a car, it will not move, or probably will move slowly, maybe. But if you push a very small ball, then it's going to be moving much faster. Okay. In chemistry, mass is also the measure of quantities of matter in an object. So that is measuring how many atoms or molecules in the object. Okay. So mass has a SI unit of kilogram. Okay, not gram. Okay, so just keep that in mind. It's kilogram. All right, and then it's not pounds. Pound actually is a unit of force. It's not unit of mass. Okay. The table here lists some typical masses in kilograms. For Earth, it's roughly 6 times 10 to 24 kilograms, okay? And then for our human body, it's in the range of like 70 or 80 or sometimes 100 kilograms, okay? And then etc. All right. But you guys don't need to remember all those numbers, okay? So when we talk about Newton's law of first law of motion or the law of inertia, then we can also bring up this concept of initial reference frames. Okay, so when we talk about the motion of an object, if it's having constant velocity, all right, so then we can use the object as our initial frame of reference. Okay, so an object that is having constant velocity, you can use it, or maybe when it's not moving, it's at rest. Okay, so when an object is at rest, then you can call it as your initial frame of reference. Okay, and then when it's moving with a constant velocity, it can also be used as an initial reference frame. Okay. Now, the counterpart of an initial reference frame, it's a non-inertial reference of frame, or frame of reference. Okay, so that is when if you treat some object as your reference frame, but it's actually having an oscillation. Okay, so then that reference frame is a non-inertial reference frame. Okay, just terminologies. Okay, over here. All right. So we'll try to see an example that can be explained by the Newton's first law of motion. Okay, so imagine if someone is transporting an open box of cupcakes to a school party. The car in front of her stops suddenly, and then she applied her brakes immediately. She was wearing her seatbelt and suffered no physical harm. But the cupcakes flew into the dashboard and became smush cakes. Okay, so we can explain this using Newton's first law of motion. So basically, when the cupcakes and the driver and the car, they are moving with the same velocity. Okay, now at the moment that she applies the brake, so her body, because she's wearing the seatbelt, her body and the car will stop or slows down quickly. But the cupcakes, they are not restrained, right? So they will they will have their initial velocity, okay? So because there's no immediate force holding the cupcakes, so they will keep moving forward, okay? So that's why they flew into the dashboard, okay, and then become smash cakes, okay? So that's because they are having their original velocity because there's no immediate force holding them, okay? All right. So if we put into equation, then this is basically what Newton's first law of motion says. So velocity equal to constant when the net force is equal to 0 or no net force on the object, okay? So it's either if it's not moving at all, so then its velocity is constant as 0, or it's moving at with a constant speed in a line, say 50 miles or 50 kilometers per hour, okay? So if this is constant, then also net force should be 0, okay? So when you see a problem, okay, so pay attention to the, when you see a problem, when the problem states the object is moving with a constant velocity, then immediately you want to refer to then the net force is equal to 0, okay? The same as if it's at rest, then net force should be 0, okay? So both scenarios. All right, now let's check on Newton's second law of motion. This is something we can actually infer from our daily experience, right? Think about, so if like two friends are pushing on the this cart here with a child sitting on it, right? So you can see they probably can isolate this cart faster than if there's just one person pushing on the car, right? So if you can add more force to the object, then the changing of the velocity will be more dramatic than if you are just applying small forces, right? It's easy to understand. So from there, you can conclude that acceleration then should be proportional to the force or the total force you apply, right? Okay. Also, another scenario, as I mentioned earlier, if you use the same force, you are pushing on a lighter object versus pushing on a heavier object, then you will see that the lighter object will oscillate faster than the small or the heavier object, right? So in that case, you can say that oscillation then is inversely proportional to the mass. Actually, it's not force. That's a typo there. Let me see if I can change this. Oh, it's a picture. Okay. Yeah, so make a note here. It's inversely proportional to the mass. Okay, this is also a picture. Okay, so I will change it later, but you can see this is probably this should be just the mass. Okay, inversely proportional to the mass. So combine those two statements. Acceleration is proportional to the force you apply. It's inversely proportional to the mass. So then you can easily arrive at this conclusion. So the acceleration then should be proportional to the force and then inversely proportional to the mass, okay? So you can set this up. Acceleration then is equal to force divided by mass, okay? That's what Newton actually, he proposed, okay? So if you were born like a few hundred years ago, you probably can write that too, right? So, but anyway, so if you rearrange the equation over here, you put force in one side and then mass to the other side. So then you will have force equal to mass times acceleration, okay? So in this case, you can see this is force is equal to mass times acceleration. And then if you check the dimensions of force, if it that is in newtons, right? So newtons then is equivalent to kilogram for the unit of mass, and then meters per second square for the unit of acceleration. Okay, so that's why 1 Newton is equivalent to 1 kilogram times meters per second square. All right. Now, many times when you have an object, it's actually having multiple force on it. Okay, so then many times you'll be looking at the net force on the object. Okay, that equals to mass times acceleration. All right. So in the previous scenarios, when we just have single force, then F equal to m times acceleration. But in many cases, it's summation of all forces, or we call net force. Okay, so when you see this sign, this is summation sign of the forces. That means net force. Okay. Other systems of units here. So SI units, that's what we been using constantly throughout this class. And second one you may encounter often when you are in other class, or I guess you guys did this in lab too, is the CGS units, when you have centimeters as the length, and then gram as the mass, and then second as the time. Okay, so that's the CGS unit. In that unit system, force is in dyne. Okay, and then British units, in British units, force is in pound. Okay, and then acceleration is in feet per second square, mass is in slug. Okay. All right. So because we just learned Newton's second law and first law of motion, and earlier we learned about kinematics, so one-dimensional kinematic and two-dimensional kinematics. Okay. So we are going to combine Newton's laws and then kinematic here. Okay, for the two exercises here. But we will start with just one-dimensional motion. Okay, to make life easier here. So the first one here says a 92 kilogram water skier floating in a lake is pulled from rest to a speed of 12.0 meters per second in a distance of 25.0 meters. What's the net force exerted on the skier, assuming the acceleration is constant? Okay. So we just learned Newton's second law, named net force equal to mass times acceleration, right? So if you are looking for net force, then you have the mass provided, but now the question is, what's the acceleration, all right? And then given the information you hear, and then the one-dimensional kinematic, I think you guys should be able to figure out the acceleration from one-dimensional constant motion, okay? So basically, you'll be looking at the equation of motions for one-dimensional constant motion, and then you will be able to figure that out, okay? So I'll have you guys take try this one, okay? And then we can take a look at the solution in a few minutes together. The next exercise is very similar to this one. Okay, so if you finish the first one, you can go ahead and then do the second one. All right. So I think most of you guys are done with the first one. We can take a look at the solutions here together. Okay. So as I said, we are looking for net force. Okay. So net force. So you can use summation of force as net force, or you can, it's up to you, or you can say F sub net. Okay. That means net force as well. Okay. So either way, but it's going to use equal to mass times acceleration. We know mass is 92.0 kilograms, then we need to figure out the acceleration. Okay. Now it says the distance it traveled is 25 meters. And then it says it's been pulled by the force, net force there, and then travel 25 meters, has a velocity of 12.0 meters per second. Okay, so that's final velocity, and then initial velocity should be 0. Okay, so then this is distance travel. So if you put the original position as x naught and then final as x, and then you can set your origin at the initial position. Okay, so then d will be equal to x minus x naught. Okay, x minus x naught is 25. All right, and you can check with your one-dimensional constant motion, the equation of motions, those 5 equations we mentioned earlier. So you probably can determine that or figure out that you will be using the 5th equation for one-dimensional motion to figure out your acceleration, because the 5th equation says final velocity square equal to initial velocity square plus 2 times acceleration x minus x naught, right? So you have this guy, this is initial 0, this is 25, okay? And then this is 12. So 12 square equals to 2 times 8 times that. So you can figure out your oscillation. So your oscillation here then will be equal to the V squared divided by 2 times x minus x naught, okay? So 12.0 squared divided by, or meters per second squared divided by 2 times 25 meters. That gives you your oscillation of 2.88 meters per second squared, all right? Then use that, you can figure out your net force equals to the mass times the oscillation, okay? So 65 newtons, okay, if you keep 3 digits, okay? So you'll probably figure out the units is kilogram times meters per second squared, but that's equivalent to newtons, okay? So if you use everything in SI unit, then the final quantity should also be SI unit, okay? If you know that should be in newtons, okay? All right. Any questions you guys might have? All right. So then we can take a look on the second one here. The second example on the last slide here, it says, in a grocery store, you push a 15.4 kilogram shopping cart horizontally with a force of 13.4 newtons. Ignore the friction force if the cart starts at rest. How far does it move in 2.5 meters? Okay, so on this one, let's look at the solution together, but let's start with a sketch here. Okay, so let's do it this way here. So you're pushing a shopping cart. Okay, with a force 13.4 newtons. All right, the mass of this cart is 15.4 kilograms. Okay, now let's see if we can come up with the free body diagram on this one first. Okay, because that's one technique that we just mentioned earlier in the class. So you can imagine what are all the forces on the cart over here, right? So it says there's this pushing force. Now there should be weight. Okay, there should be the supporting force from the ground to the car. But these two will cancel out, okay? They should have the same magnitude in opposite directions. So those two will cancel out, okay? So then from here, you can see if you are drawing the free body diagram, you'll probably like put a dot here and then say weight and then the supporting force, and then those two will cancel out. You can put it in that way. And then there's this force, pushing force, normal force, okay? So you can, this is how you can move it over here, because if you keep then the same length and then just move it, parallel it over, then it's the same force, okay? So then that would be your pushing force. So this will be your free body diagram from the cart, okay? All right. But let's take a look. It asks us how far does this car travel in 2.5 seconds, okay? So it's asking, so if you start this as your original position, let me call this X, okay? So then you'll be looking for after t equal to 0.5 second, where's the final X, right? You're looking for final X. So yeah, then you'll look, check at those equation of motions, all right? And then you see from free body diagram, you can see this pushing force is your net force. It says the friction force is negligible. So then that's your net force, okay? So you can see net force equals to mass times oscillation. So from there, you can figure out your oscillation, because net force then is 13.4 over the mass of 15.4 kilograms, okay? That will be your oscillation equals to net force over m, okay? Then goes there, plug in the numbers, goes there. So then that gives you 0.8701 meters per second square, okay? So this is your oscillation. By giving you the net force and mass, you can figure out your oscillation quickly, okay? Then you'll be looking at your 5 equation of motions, and then you're looking for x. You probably figure that you can use this one, the force equation, to figure out your x, right? This is 0, initial velocity is 0, or initial speed is 0, okay? Because you just push it, you will start to move, okay? Then this is equal to 1/2 of 0.701 times 2.50 seconds square, okay? So then x is roughly 2.72 meters, okay? That's how far the car will move, okay? Any questions you guys might have? All right. So if not, we'll stop here for today, okay? And I will see you guys on Friday.